The dispersion of a distribution is the width of the distribution. How spread out are the scores? How dispersed are the scores? The range is an indicator of dispersion, and so is the standard deviation. The standard deviation is nice because the units are standardized. That is, they are not in IQ points or beats per minute or happiness numbers or neural activity or whatever. In the same way, because they are standardized, we can compare results across different measures. So the standard deviation units in beats per minute has the same meaning as standard deviation with IQ points. If we look at the formula, what we see is that you take one score, an observation, subtract it from the mean. That's what that little bar on the top means. So how far is the score from the mean? And then we square it to get rid of any negative numbers. Okay, so how far are the scores from the mean? We sum that up. If scores are all really, really far from the mean, then this number is going to be really large on top. And then we scale that by however many subjects we have, -1, and we do the -1 to account for degrees of freedom, and that's something that's talked about more in your textbook, and you can check that out if you want. But essentially, we're looking at how far the scores sit from their own mean, divided by taking the average of that. Okay, we're dividing by the number of observations that we had. And then we take the square root of that. The z-score is a standardized score that is based on how far the deviation of a single score is from the standard deviation of a set of scores. So a z-score of 3 for a measure of happiness, again, a z-score of 3 for a measure of happiness and a z-score of 3 for a brain response can be considered comparable. Okay, they're the same units now. They are relative scores that describe how far out a score is relative to the rest of the scores. We're describing a data point using the normal distribution. Okay, so if we look at the formula here, how far is this score that I'm going to make a z out of, how far is this score away from the mean relative to how far the scores are from the mean in general, this standard deviation? Okay. One way to compare groups using normal distributions is to use confidence intervals. So if the scores are normally distributed, then we know that 95% of the time, or 99% of the time, or 99.99999% of the time, that the true mean is included in this distribution. And we know, because we know how the normal distribution is supposed to be shaped, actually we can go back here, you can see that about 40% of the scores lie within the first, negative half a standard deviation and positive half a standard deviation. And then if you added up all these percentages between 2 and -2, this would equal about 95%. That's where the scores should lie. And we can keep going out on the distribution if we want to get more and more confidence. So a z-score of more than 2, like here, okay, the z-score from group B, the average z, is at 3 standard deviations, or a z-score of 3, and that's far outside the 95% confidence interval that we would usually use. Usually people use a 95% confidence interval. And you can just remember that a z of 2 is 95%, 1.96 or 2. It's pretty darn close. So in this case, there may be an effect that's driving the larger z-scores on average for group B here. Okay. They have an average z of 3, whereas this group has an average z of 0. So now we're going to move on to basic statistical models. Well, what is a model? A model is just what we use to describe the data we've collected. And you've used models before. The average, the mean, the median, the mode, the range. These are all models, although they're pretty poor fitting models, okay? And there's a little bit on model fit in your textbook. Oftentimes what we do in statistics is compare a poor fitting model like the mean with a model that we think predicts the data better than the mean. So let's go back to our coin example. How could we compare the fairness, or how could we evaluate the fairness of a coin? We won't look at 2 coins, we'll just say. Let's say we toss 2 sets of coins. Let's say we toss a coin, coin A here. Okay, and let's compare the expected mean number of heads from a fair coin with the expected heads from a coin that is biased to 70% heads, let's say. In that case, so the expected heads from a fair coin would be 50%, and a coin that's biased would be 70% heads. So does the average from coin A, as shown here with this data, does the mean from coin A, does the bias, the 70% bias, predict the data better, or does the mean of the expected heads, the 50% heads, predict the data better? Well, it's clear that coin A's data fits, or the bias, the idea that the coin is biased, 70% biased, the model that it's 70% biased fits this data better. In fact, it fits perfectly. However, this is only after 10 flips. This could easily be due to just a chance. Okay? We aren't comfortable making the inference based on 10 samples that all of the coin A's in the world are 70% biased towards heads. Right? We wouldn't be comfortable saying, what, 7 out of 10, all the coin A's in the world must be 70% biased towards heads. We probably wouldn't feel comfortable saying that. However, if we flip the coin 10,000 times and it came up heads 7,500 times, we may have more confidence in that inference. We may have more confidence saying that, well, coin A is a coin that's biased to about 70% heads. It came up 7,500 times heads. After we flipped it 10,000 times, we have a pretty good case. In this regard, the sample size is very important for drawing inferences from data. The more data that we have, we can be more confident in our inferences about the population, about what's going on in the population, and it's not just a chance fluke of the sample that we got. We determine how well a model fits the data by computing the sum of squared errors. This is also called the least squares approach. We calculate how far each score is from the score predicted in our model. So y here, well, this is basically, you can see it here, how far each of these data points from the mean, let's say the mean is 7.5 here in gold, compared to this line of best fit here. If we squared up the deviations, the distance of these points from the mean and from the line of best fit, which one is going to have the smallest sum of squared errors, or the smallest variance? We calculate how far each score is from the score predicted by our model. In this case, it could be a mean or a regression line. And the SSE, or the sum of squared errors, is relative to the size of the sample. Okay, this is how we get the variance. We divide the sum of squares, because if we had a large sample, this would just get really large, and it would be more a product of the size of our sample than the data itself. So we scale the sum of squared errors by the number of observations that we have, and that's called the variance. And the model with the smallest variance wins. We also say the better model accounts for more variance. We've captured something in the data, and that's why our prediction is better, and it's accounting for more variance. We only use a more complex model if it accounts for a lot more of the data, a lot more of the variance. And we actually take a drop in our ability to say that an effect is significant, to say that an effect is real and reliable, when we add complexity to our models. So there's a bit of a trade-off between model simplicity and then how much variance we can account for. When we compute statistics, we can choose how liberal or conservative we want the tests to be in terms of saying that this effect is significant or non-significant. The type 1 error rate is the rate at which our statistics will find effects that aren't real, that are only due to chance. Remember the coin flips. 7 out of 10 flips landing heads has a high likelihood of being a chance effect. But if you had a high type 1 rate, you may say it's an unfair coin. The type 1 error rate indicates how many false positives you're going to find per 100 tests that you compute. If your error rate is 5%, then for every 100 tests that you compute, 5 of them are going to be erroneous. The type 2 error rate is our false negative rate. We make a type 2 error when we fail to detect an effect that is true or real. In this case, if you had a very high type 2 error rate, you might conclude that a coin is fair even after it came up 75 heads out of 100 flips. Type 1 and type 2 error rates refer to hypothesis tests. A hypothesis test is either significant or it isn't. A hypothesis test can't be more significant or less significant. It either is or it isn't. The effect size is an indicator of the size of the effect. It tells the researcher how much they were able to predict with their model. So far, we've only really talked about parametric statistics. All that stuff about normal distributions and the central limit theorem, those things are parameters. There are other parameters. Some of the different tests we use compare the data to slightly different distributions of parameters. There's a t-distribution, f-distribution, chi-square distribution. Parametric statistics also assume homogeneity of variance and independence. Homogeneity of variance can be improved by transforming the data sometimes, or by using statistical adjustments. Observations must also be independent from one another. They can be dependent on one another in lots of different ways. Studying a pair of twins, studying a couple, studying a person or on multiple occasions, those are all cases of dependent observations, okay? One observation has something, it can have an effect on the other observation. We'll learn about these repeated measures designs later, but for studying people across multiple occasions. And here's just an example of heterogeneity of variance. So in this case, the assumption has been violated. In this case, the assumption has been met. This is heteroscedasticity or homoscedasticity, or just another way to say homogeneity and heterogeneity of variance. And these are an example of how it might look in real data. In most cases, violations of the assumptions will be due to outliers. There's no right way to deal with outliers. It just takes judgment on your part to decide which cases to leave in or out, and it depends on the hypotheses of your experiment. You can remove weird cases, transform the cases, take the square root, and there are other ways to transform the data. Then you can check your new histogram with the new data and see if it looks more like it satisfies the assumptions of your statistics. Thank you.